Welcome, Hornets. Today we're going to be going over a few more of our derivative rules and just trying to get better and find more formulas that will allow us to do well. Now, a couple of things I do want to make sure that we understand is the notation that I'm about to use. If I take the derivative dx of y, I end up getting dy dx. We also know that if I take the derivative d dx of x, I end up getting dx dx, and we've called that 1. So please keep that in mind. You're also going to see a situation which is a later discussion, in fact, tomorrow's lesson, on the chain rule. But the chain rule is actually going to happen a little bit today. Let's just talk about what the chain rule is first. So the chain rule is the big beast in the pond, okay? If you want to think about it, it's the shark in the pool. It's the thing that you have to watch out for. And the whole idea is composites. F of g of x. Now, I'm going to go ahead and put my d dx in front. Now, as we've seen, especially with limits, we take the limit of the derivative inside, and then we just apply whatever we get into the f of x. Well, we have to deal with almost a reverse situation now. What we're going to do is we're going to find the derivative df dx, and we're going to leave the inside g of x alone. And then we're going to multiply by the derivative of g of x. Now, this can be difficult. It does have its moments, and there's no way to hide from it. We're going to see it all the time. Now, we're still dealing with our explicit differentiation. Explicit differentiation is when we have the same variable through. Implicit differentiation will have a different variable. Working with dy dx, for example, is an implicit differentiation, whereas dx dx is explicit. So let's take a look at the first rule I want to find. I want to find the derivative for the natural log of x. Why? Well, we've already seen that the derivative of e to the x is itself. And so I'm hoping maybe I can use that in an effort to figure something out. Now, we're going to start off with y equals, and we have our natural log of x. This is the case whenever we are dealing with exponentials of any kind. Be aware of that. This is going to be consistent for AB, BC, and even beyond, and a lot of other places. So, we're now going to start with an exponentiation. We're going to exponentiate both sides because we know e to the y, and this is x. This is one of our special rules that we've had. You saw that last year. Now, it's at this point that I'm going to take my derivative because I know that e to the x is e to the x. I'm going to take the derivative on this side as well. So we're looking at d dx of e to the y equaling d dx of x. All right, let's keep going. So our next step is to apply our chain rule. See, I have e to the x and there's a y there. So I'm going to get the derivative of e times the derivative of the inside piece. And this will equal 1. Now, my goal was to find the derivative of y, which would give me the derivative of the natural log of x. So I'm going to keep going and simply multiply by 1 over e to the y. 1 over e to the y. Well, this gives me my dy dx. That's what I'm looking for. And I end up with 1 over e to the y. But remember, y was the natural log of x. So let's just do it up here so I don't have to get too close to the edge. I'm going to take dy dx, and I'm going to substitute e to the natural log of x. Well, we've already talked about that. Right? Remember? That was right here. That's just x, e to the natural log of x. And I ask, can it be that simple? Is it simply 1 over x? Well, the process itself is not necessarily the simplest thing to deal with. That's reality. But if I can go directly from the natural log of x to 1 over x, that is easy. And that is our goal. So there's our first derivative, using the derivatives that we currently have. Let's take a look at another one, but we'll do that in our next video. Thank you very much.